The periodic table is a tool that you'll use a lot in this course. So we're going to look at it, how it's organized by metals, nonmetals, and metalloids, how the groups and periods are arranged, various trends that you can predict from the periodic table, and then we'll look at special group names. On the periodic table, you have all the known elements arranged by symbol, and they go horizontally by atomic number. And so as the atomic number increases, you will move down the periodic table going through the rows. The way this table is organized helps predict the properties of the atoms that are found there. So often elements in a certain column or a certain row will have predictable properties based on where they're located. So here is your periodic table. You'll notice that they have it arranged with the numbers going up sequentially. So we have hydrogen at 1, helium at 2, lithium at 3, beryllium at 4, boron at 5, carbon at 6, nitrogen at 7. So the number for the atomic number goes up 1 as you go across the rows, and then they'll go down and start again on the next row when you reach the end of a row. Your metals are located in the lower left-hand side of the periodic table, and in this one that we have here, they're indicated in pink. Your metals tend to be shiny. They are good conductors of electricity. They're malleable, which means you can bend them. They're ductile, which means you can draw them out into wires easily. Most of them are solids. Mercury is the exception that most people know, but gallium and cesium and francium are also really close to being liquids at room temperature. So you just heat them up a little bit and they turn into liquids. Your nonmetals are located in the upper right-hand side of the periodic table, and hydrogen is also a nonmetal, even though it's located on the left-hand side. So we'll look at those there in yellow. So you'll notice that hydrogen is the only yellow one on the left-hand side. And then the upper right-hand side, they are also yellow. So those are called nonmetals. Nonmetals have different properties than your metals. They tend to be dull in color or transparent. A lot of them are just entirely see-through. They are poor conductors of electricity, except for carbon, which does conduct electricity. They're brittle. They shatter easily. If you were to hit them with a hammer, instead of seeing the imprint of the hammer there, they would shatter in a million pieces. So if you take like a chunk of sulfur and hit it with a hammer, it goes everywhere. And at room temperature, they're found in all three phases as a group. Each one has its own phase that it's found in, but you get solids like carbon and sulfur and phosphorus. And you get liquids. Bromine is a liquid. And then you get gases, your noble gases, so neon, argon, helium. Hydrogen also comes as a gas. It comes as H2 though, instead of as a single element. Oxygen comes as O2, nitrogen comes as N2, fluorine comes as F2. They're gases. And then we have our metalloids. The metalloids are located between the metals and the nonmetals, and they're indicated in green on our periodic table here. You'll see that there's a few of them there: boron, silicon, germanium. Usually people have heard of silicon more than anything because it is the less expensive between silicon and germanium, and so it's used with a lot of electrical things for computers. So they use these because they have properties between a metal and a nonmetal. They use them to make semiconductors. What that basically means is when you run electricity through a metal, it goes through really well. You run electricity through most of your nonmetals and it doesn't go anywhere. It's an insulator. You run it through a semiconductor and under certain conditions it will go through and under other conditions it won't. So you can use these elements as switches. Put it under one set of conditions, the electricity goes through. Put it under a different set of conditions and the electricity does not go through. so they can use them as little tiny switches in your electrical circuits. The periodic table is organized by periods and groups. A period is a horizontal row. So the numbering of the rows on the periodic table goes down sequentially. It starts with 1 and proceeds to 7. There are only two elements in period 1, your hydrogen and your helium. And then as you go down to the next row, you have lithium through neon, that's period 2. Sodium through argon are in period 3. And the sixth period, when we get down there, it's so long that they have taken part of it and put it below the periodic table just to make it fit on the piece of paper. And the seventh period, same thing is occurring. And that's why you have those two rows at the bottom of the periodic table that look like they're not connected to anything. They actually do belong in the main periodic table, but they've put them below just so that it fits on the paper. So you'll see the lanthanide and actinide series. Those are the ones that they've put below. The lanthanide series actually belongs in period 6, and the actinide belongs in period 7. So if we were to put the periodic table together the way it should be and just kind of ignore how much paper we'd need for it, it would look like this lower periodic table here, where they've got the blue here inserted between our green and our yellow. That's where it would be on your periodic table. But to save space, we move them down to the bottom. Then we also have groups. Groups are the columns of the periodic table. They tend to have very similar reactivity, and they're numbered from group 1 over hydrogen, that column there, to group 18, which is over helium on the opposite side of the periodic table. Sometimes these groups are indicated by Roman numerals instead of by numbers, and sometimes they use an A and B system so that instead of being 18, it'll be 8A or 8B depending on how they've organized the periodic table. You'll find trends that are very predictable in the periodic table based on where things are located. So here are a couple of examples. The atomic radius. So you have an atom, it's roughly a sphere in shape. If you were to look at the size of the sphere, the atoms actually decrease going from the left side of the periodic table to the right side of the periodic table, which kind of seems counterintuitive because you actually have more mass as you're going from left to right. But the secret of that is that most of an atom is empty space. And we'll talk about this more in the future, but as it goes from left to right, the empty space between the nucleus and the electrons that are on the outside making your sphere decreases. But as we go to the next period or the next row in the periodic table, that trend repeats, but the starting radius is larger and the ending one is also larger. So as you go down a group or column, the radius is going to get bigger. Another is electronegativity. This is the pull for extra electrons. Some elements are better at swiping electrons from other elements than other elements are. So if you go from the left to the right across the periodic table, you have an increased pull for electrons. So fluorine is actually the best at swiping electrons. As it turns out, group 18, the noble gases, they're perfectly stable, and so they don't like to take or give up electrons. So we just kind of ignore them when we look at electronegativity. And that electronegativity decreases going down a group. So the ones at the top have the highest electronegativity, the ones at the bottom of a column, the lowest. There are some special group names. So your group 1, which starts with hydrogen, and then you have sodium. Hydrogen usually isn't lumped with them quite so much since it's a nonmetal, but the rest of them are called alkali metals. They call them that because if you take them and put them in water, particularly the ones at the top, react violently. And when they react, you get flames shooting out. and you have a basic solution when you're done. So if you put sodium in, it turns into sodium hydroxide. If you put lithium in, it turns into lithium hydroxide. So these are bases, very strong bases. And if you were to check the pH, you'd find out that it was a really basic solution. They have to store your alkali metals really carefully because they tend to be flammable like that. So if you were to have a building where you had a lot of sodium, a lot of lithium, something like this, they actually have to mark it for a firefighter, because if you have a fire start there and you come and bring water and you try to put it out with water, you could actually make the fire go bigger. And that's happened before at fire sites at chemical plants. So they have to instead put the fire out with something that would extinguish oxygen instead of adding water. The groups 3 through 12, that center block in the periodic table, are called your transition metals. And the lower ones, the sixth and seventh, that we've kind of taken off the periodic table and set at the bottom, those are called your inner transition metals. And the sixth is called the lanthanides, and the seventh is called the actinides. And they call the sixth lanthanides because they come after lanthanum, and they call the seventh actinides because they come after actinium. Actinium. Group 16 are the chalcogens. That means ore forming in Greek. Group 17 are the halogens, which means salt forming. And you'll actually be familiar with some of the salts, like sodium chloride. You'll find chlorine in group 17. And then group 18 are your noble gases. And that's because they don't react with other elements, just like nobility doesn't mix with the lower folk. And they also sometimes call them the rare gases. They call them that because they don't react, and so it took them a long time to find them. And they could predict there should be an element there because they could number the protons and figure out, there should be something here that we haven't found yet. But they couldn't find them because they don't react with anything. And they finally were able to find them by isolating some gases and running electricity through them, and then they got really pretty lights coming off of these elements, and they were able to see that something was there. You're probably familiar with neon signs, which are an example of the red ones. You're running electricity through neon, and it gives us really pretty color.